Welcome to part two of our lecture video series for Monday, May 8th, where we are going to look now at the temperature dependence on vapor pressure. So let's begin by reminding ourselves about the relationship that exists between temperature and pressure for just like regular straight up pressure. So we're not looking at vapor pressure anymore, we're just looking at regular pressure. So recall, from our analysis on gas relationships last week, we came to understand that pressure and temperature are directly proportional, meaning if I were to increase the temperature, I should see a corresponding increase in pressure, and vice versa. If I were to decrease the pressure, I should see a corresponding decrease in the temperature, or again, vice versa. So mathematically, what is that structure? So if I were to remind myself of what it means to be directly proportional, variables that are directly proportional to one another have a quotient that is equal to a constant. That is what it means to be directly proportional. And for us math folks, if we were to rearrange this so that it looked like some kind of function, we would see that pressure is equal to some kind of constant, whatever that constant is that relates temperature and pressure, times temperature. So this is what a direct proportionality looks like mathematically. This is its kind of formulaic structure, functional structure. There we go. All right. Well, hey, this formula structure is y is equal to n times x, right? Dependent is equal to constant times independent variable. Meaning if I were to look at a plot of how temperature and pressure are affected, then I would see that for every change in temperature, there is a correlating proportional change in pressure, meaning I would see a linear function. That's what it means to be directly proportional. However, what about vapor pressure versus temperature? What is it about vapor pressure and temperature that might be a little bit different than looking at a plot of just pressure against temperature? So, turns out that vapor pressure and temperature are not directly proportional. In fact, they show an exponential relationship between one another, meaning that as there's some incremental or small change in temperature, there's going to be a really large change in our pressure, especially at high temperatures. So once we kind of deviate away from, I don't know, let's say this temperature, where this, I think we could argue, looks a little bit like a straight line, we see that at high temperatures or at increasing temperatures or as temperature increases, the vapor pressure wildly increases exponentially. So instead of seeing this kind of one-to-one proportional relationship between temperature and pressure, vapor pressure sees an exponential relationship. Well, why is that? Why? Let's think about what's going on when we're talking about vapor pressure. So recall, anytime we're talking about vapor pressure, we're talking about a liquid that is in some kind of closed or an approximately closed system. So I'm just going to draw a box now. I'm not going to try to convince you that you've got a Nalgene bottle to consider. All right, so let's look at our liquid at T1. So that's some temperature. So at T1, there is going to be a phase equilibrium that is established between the gaseous and the liquid phase. So I will see some amount of gas particles or vapor particles found in the headspace above the liquid. And then as I increase that temperature, I would see that the level of my liquid would get lower because I have now shifted the equilibrium in favor of producing gas particles, right? If there's more energy in the system, then there's going to be more statistical likelihood that our liquid particles encounter that gas phase or gas liquid boundary and escape into the vapor phase. So if T2 is higher than T1, then we should see that. But what if we were then to take our system and bring it all the way to its boiling point? So at the boiling point, we would no longer have any vapor pressure, or sorry, any liquid left in the system, because at that boiling point, there might be a very slight quantity, like super slight. Talk about that later. But at that boiling point, we're seeing a major domination of gas particles compared to our liquid particles. So as we increase temperature, not only is the number of liquid particles available to escape into the vapor phase decreasing because we've shifted our equilibrium such that it favors that vaporization phase change, we're also now looking at putting a lot more of those gas particles into our closed container. And that is going to see a huge spike in our vapor pressure. So much so that, by definition, the boiling point of a liquid, the temperature at which a liquid begins to boil, this is the temperature at which the vapor pressure of the liquid is equivalent to atmospheric pressure. So if we think about what it would take in terms of energy, thermal energy, in order to get a cup of acetone to completely vaporize, whatever pressure that those acetone particles exert once they've been completely vaporized at that temperature, we call that temperature the boiling point, and that pressure, the vapor pressure, would be the same as the surrounding atmosphere. So the boiling point of a liquid, by definition, is where the vapor pressure of that liquid is equal to atmospheric pressure. So we see this exponential increase, not proportional. So how then do we model that exponential relationship? Well, we do so using my favorite equation in the sense that it is so much fun to say. We use the Clausius-Clapeyron equation. And the Clausius-Clapeyron equation is an equation that relates the vapor pressure of a liquid to temperature. This is going to depend on a couple of things. First, the gas constant, R, which here we express as 8.314 joules per mole Kelvin. So this is no longer liter atmosphere per mole Kelvin, it's just a different value that's been converted to have this new unit. And why is it that we have this new unit being joules? And that's because we have to consider the fact that phase changes are not something that happen without any kind of energetic prompting or setup. Meaning, like, if I want to make water go from being liquid water to gaseous water, aka steam, I've got to pump that full of thermal energy in order for that water to boil and then become steam. And that energy requirement is something that's known as the heat of a phase change. So here, in this case, since we're looking at the relationship between vapor pressure and temperature, we need to look at the heat of vaporization. In other words, this is the energy that is required to convert 1 mole of a substance to, to its vapor phase or gas phase from the liquid phase at some T. And we're going to get into these a lot more. You've seen the heat of fusion a lot in homework number 10. Here we're now talking about the heat of vaporization, or the energy required just to undergo the phase change. So let's look at the structure of the Clausius-Clapeyron equation. So the Clausius-Clapeyron equation, because we have this exponential relationship, is going to look a little funky. So first and foremost, I want to preface this with like a little spiel about why it is that we typically don't see exponential relationships in chemistry. So like remember when we were talking about pH, we said that for some tiny change in concentration, there was a massive change in the pH. So we kind of had to crunch down that exponential relationship between concentration of acid and and acidity by using that log-based scale of pH. Same idea here. Human beings are not really great at dealing with exponential functions. Like exponential functions are kind of hard to conceptualize. They're nice and easy to visualize, right? But if I had to actually mathematically give you a function that described the exact manner in which this kind of exponential trend occurs, that's something that's a little bit tedious. Any one of you that are in calculus could understand. So to undo this, we are going to apply the inverse of our the inverse of our exponential relationship between vapor pressure and temperature. And the inverse function of an exponential is a logarithmic function. So if I want to look at how the vapor pressure at one condition or one temperature changes at some new condition, then I'm going to look at the natural log of this fraction, and that is going to be equal to the negative heat of vaporization over R times 1 over T2 minus 1 over T1. So this is the Clausius-Clapeyron equation. Now, I've told you that my advisor, in her infinite wisdom, says that chemists are cheap and lazy. Another thing that she says that is absolutely true, and in 220 you will find this is something that I'm not lying about, it is that chemists like straight lines. We understand and can look at trends and can quantify how how straight a straight line is. So we're going to look at what this function would be if I were to plot, instead of just vapor pressure versus temperature, what if I plotted the natural log of vapor pressure against inverse temperature? So if I were to look at this plot, this would be a straight line, which we like, right? Straight lines are a little bit easier for us to kind of conceptually and then also mathematically handle and deal with. So this is the Clausius-Clapeyron equation. Yes, it's gross, but let's do some practice problems with it in our next video. So that completes our intro to the Clausius-Clapeyron equation. Let's practice it in warm-up, or not a warm-up, but a practice problem. And then we'll kind of talk briefly about phase changes because now we're getting to the point where they are unavoidable, right? We've talked about the gas phase. We're now talking about vapor pressure, which involves a phase equilibrium, meaning a change in phase between liquid and gas. So it's coming up, this conversation about phase changes in general, because we kind of need it at this point. So let's practice Kelsey's Clapeyron, and then we'll do an intro to phase change.